Okay, so let's look at some encryption where we can modify the ciphertext. So in symmetric key encryption, we have the same encryption key as we have to decrypt. So Bob will use an encryption key, Alice will have the same encryption key, and we'll be able to decrypt. So we go from plain text to ciphertext with the encryption key, and from ciphertext back to plain text with the same encryption key. There are various methods that we can use, such as AES encryption, Ciphertext, ARIA, SM4, 3DES, and so on. And they all vary in their performance and how they actually achieve the encryption. But along with the basic mode that we have, basic method, we also have different modes, such as ECB, electronic codebook, CTR, counter, GCM, Galois, cipher mode, CBC, cipher block chaining, and so on. One of the fundamental differences is that AES is fundamentally a block cipher. So in that we have something like a 128-bit block, which is 16 bytes, and we fill up each block and encrypt it. Each block gets encrypted. The last block might not be filled up, so we will have to pad before we encrypt. And then on the other side, after we decrypt, we unpad from there. Okay, so sometimes we add salt into that. In the purest form, ECB, we have no salt value, no initialization vector or nonce value. So whenever we cipher a certain input value, we will always get the same output value. Often, or most of the time, we add a salt value or an initialization vector, and which will change the cipher to give us a different output for the same input. But obviously with the same salt, we will always have the same deterministic output. So that's a block cipher, and that can be kind of slow to operate. So we often change our block cipher into a stream cipher. So ECB and CBC are block ciphers. A GCM, CTR, and so on are stream ciphers. With this, we take the block and we convert it into a stream, which means that the number of bytes that we have in our input is equal to the number of bytes that we have on our output. Stream ciphers are CTR, GCM, and CCM. These methods tend to be very fast in their operation. We can see CTR is a fast method here, nearly as fast as ECB, and we'll be using CTR in a little minute. CTR differs from GCM in that we have what's called additional data. So along with the salt, the key, and the input data, we add in some additional data into the encryption process. On the other end, we need the same additional data, and we need the same key and salt value to be able to decrypt. If we don't have those, then we'll not be able to decrypt and we'll have an exception. A typical additional data is to have a session ID that we link, which stops the cipher from being played back in another session. So we can see here the stream cipher here of CTR and GCM. The main difference with GCM is that we have some integrity, and this integrity is generated through what's called a G hash. And so that if any of the bytes are changed in the cipher, we'll be able to detect it with this G hash. With CTR, unfortunately, we don't actually have that. Ciphertext itself is a stream cipher and very efficient, pretty good performance here. overall, but we need to add in poly 1305 to be able to create an authentication tag with it. So these authenticated encryption methods are called AEAD, or authenticated encryption with additional data, and they provide a lot of integrity in the cipher. As we'll see, CTR lacks that. Okay, so let's take an example with CTR. So let's start off, and we've got a message. We're going to pay Bob $1. We're going to encrypt with a key, Bob123, and it's going to be generated through PBKDFS2. KDF is key derivation function, and it'll create a 128-bit AES key that we'll use for 128-bit CTR mode. Okay, so we'll go ahead and we'll create our cipher text. Next we'll have a look to see what it looks like, and it's in a byte form, so it's difficult to view it apart from the bit at the start, which is just describing that this is a salted cipher. So it has an initialization vector that's been generated by the cipher. So the OpenSSL has generated the salt value that's going to be used for it, and it's contained within this output here. Luckily, we can use XXD to convert it into a format that we can actually use. So let's convert our ciphertext into data. So we'll have a look at what's in there. And this is what we have. Okay, so what we want to do is to change the 1 into a 2. So there's a 1 ASCII is this bit pattern, and a 2 is this bit pattern. So the only difference is that the bits are flipped between the 1 and the 2. So when it's a 0, we change the 1. When it's a 1, we change the 0. So in the cipher, we'll identify where 1 is, and then we'll flip the least significant bits. So I'll just do that. So we'll just count along. So we're going 1, 2, 3, 4, 5, 6, 7, 8. So we want to move 8 characters. We don't start from here, we start from here. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we've got E9 here. So a 9 is 1, 0, 0, 1. Okay, so I need to flip the bits so that becomes a 0 and that becomes a 1. So we have an 8 and a 2, which is an A. So the 9 becomes an A because we're flipping the 2 least significant bits. Okay, so just to check that we've changed the value, that's fine. So the value that we've changed is here. So we've now got 1, 0, 1, 0, which is an A or a 10 in decimal. So we'll convert that back into ciphertext. Okay, so maybe difficult for us to see from our ciphertext now what's changed, but it's somewhere around here that we've changed the value. It's just coming up with a question mark, so we can't actually see what the value is. So now we'll go ahead and we'll see if we can decrypt this, and we'll see what we get. So we're going to take the ciphertext that we just created. We're going to use the same key using PBKDFS2, and we're going to decrypt it, which is a -D option. So fingers crossed to see if this is going to work, and it has. Okay, so you can see the lack of integrity has meant that we can actually flip bits in the cipher and still produce a valid output, which really isn't very good. So if possible, CTR mode, ECB mode shouldn't be used. GCM is still possible, but extremely difficult to do what we just did If we did this in GCM, it would come up with an exception to say that some bytes have changed. And the same with Cha-Cha 20, Poly 1305. There is an integrity check on the cipher. Okay, so thanks very much for listening, and hopefully that's given you a good example of why it's so important to have an integrity check for your ciphertext. Thanks.